Hi, and welcome to yet another e-learn session with chemistry, brought to you by the Division of Education, Innovation and Energy. My name is Isomers, and I will be teaching you chemistry today. What have we observed as chemists? All right, you have observed as many organic compounds have the same molecular formula but different structural formula. So they are substances. They have the same molecular formula, C5H12, but they are built differently. So it's like you have a Lego set and you have 100 pieces of Lego and you build a helicopter with it. Then you switch that and you build a house with it. Okay? Do they all have the same number of pieces? Yes, they do, but structurally they are not the same. So what happens? It's the same case for organic compounds. So we can have organic compounds having the same molecular formula, which is the same number of atoms, carbon, hydrogen, oxygen, whatever the case may be, and they are structurally different. All right, so that is, their molecules contain the same number of atoms of each other element, but these atoms are bonded together differently. And we have an example right on the side here. So we have this beautiful picture looking like a transformer in some ways. So we have one looking like a caterpillar and the next one looking, so you can observe that they are different. They are not the same. All right, so these blue ones would represent carbons and these white ones would represent hydrogens. Okay, so they do have the same number of carbons, which is 4, C4, 1, 2, 3, 4. They do have the same number of hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they do have the same number. But as you observe, they are not structurally the same. So they are not, in this way, they do not behave the same way. All right? And they have differences. All right, so let's take a deeper look at this. Before we go on, let me just erase here so you can see this definition clearly. So, as I always say, there are definitions that are very important for you to always have on the tip of your tongue and for you to know. This is one. What is a structural isomer? So, structural isomers are compounds which have the same molecular formula but different structural formula, and we just explained why. And lastly, we have structural isomerism. So this one here is the occurrence of two or more organic compounds with the same molecular formula but different structural formula. But you say, sir, basically looking like the same thing. Ism? No, the ism is the occurrence. All right, because as we will learn as we go ahead, that there are some organic compounds that do not exhibit structural isomerism. All right, so but they are generally, most of them, they will have structural isomerism. All right, so structural isomers. So as we continue, structural isomers can belong to the same homologous series or to different homologous series. So yes, that is true, and we're going to observe this as we go down. They can be in the same homologous series or they can be in different homologous series. So if they contain the same functional group, they will belong to the same homologous series, and of course that is pretty much straightforward. All right, they have similar chemical properties. That is because they belong to the same function, the same homologous series, and that's because of the different arrangement in the organic structure, they will have different physical properties. So I'm going to give an example here. So we have two compounds here. We have both of them belong to the same homologous series. Reason being because they both have the same functional group, OH, but they are structurally different. All right, so they will have the same chemical properties, yes, because of the functional group, but they are going to behave differently. And we're going to see some more examples where they would definitely behave differently in terms of physical properties. All right, so why did we say physical properties, they behave differently? One, because of the changing in the functional group, the compound itself will behave differently. So one might probably be liquid at room temperature and the next one may not be. All right, so one may have a very high boiling point and the next one would have a lower boiling point. So those are physical properties that may be different between these organic compounds. So let's look at those that are of different homologous series. So we have another example. So if they contain different functional groups, they belong to different homologous series. And that is of course straightforward. They don't have the same functional groups, so they won't be in the same homologous series. Now, because of this, they have different chemical and physical properties. So let's give an example. So we have two compounds here. One belongs to the alcohol series, as we have the OH, and the next one belongs to a series which we call ether. Of course, we're not going to really go into it, but you would see it later on when we get into polymerization. All right, so we have these being two different compounds. So let's take a look. So how many carbons do they have? They both have two carbons, C2, so they have the same number of carbons. Do they have the same number of hydrogens? Let's go 1, 2, 3, 4, 5, 6. Yes, there are 6 hydrogens and there's 1 oxygen. And in this case, well, 1 here. And in this case, 2 carbons as well. And we have 6 hydrogens. And we have, so they do have the same molecular formula. Remember, we say the molecular formula just shows us how much atoms we have within a particular compound. All right, so now what else can we get from here? So we say that they differ with chemical properties as well as physical properties. So let's look at the first one. So the molecular formula again, as we have it there, and then we have them in this case in terms of their chemical and physical properties. So the first one is found in alcoholic beverages and is also a nerve system depressant. Okay, and it has a boiling point of 78.5 degrees Celsius. The other is non-toxic and is used as an anesthetic at high concentrations. And it has a boiling point of negative 23 degrees Celsius. You see the difference? They do have the same number of atoms, of elements within their molecular formula, but because that they are structured differently, they will behave differently. And that's something that you need to always remember when we are dealing with chemistry and in general. All right? So, structural isomerism in alkanes. So let's look at them. So one, remember, alkanes are hydrocarbons where all the bonds between carbons are single bonds. All right? So we're going to draw out some structures. We're not going to draw all of them. So we're going to just look at those and see if we can have structural isomerism for each of them. So let's look at the first one. All right, so the first one we have, it's methane. And methane has 4 hydrogens in it, and this is how it's bonded. So I'm just going to leave the hydrogens out in this case for time, but it's understood that these hydrogens would be here. Can I draw this in any other way? No. All right? There's no other way I could switch this. I could try doing it all different way. I could flip it. I could do it. It's going to still be CH4, and it's going to still have the same structure. Okay? Let's look at the next one. So, one question here which asks, does methane have structural isomerism? The answer to that is no, because structural isomerism is the occurrence of 2 or more structural isomers, all right, from compounds having the same molecular formula and different structural formula. All right? So let's take our next look at the other one. So we have C2H6. So we're dealing with alkanes here. C dash C, and we have our hydrogens connected. So next question, can I draw this any way differently? Some people say, yes, sir, you can make it look like this. Okay, so if I make a Lego helicopter and I turn the Lego helicopter vertical, does that make it no longer a Lego helicopter? The answer to that is no, right? Because it's still the same structure. So we have to observe how we switch it around as well. It's going to still be the same thing. It's a carbon connected to a carbon, all right, connected to, and each of them having 3 hydrogens around them, all right? So it's going to be the same thing. So in this case, this one here, which is called ethane, has no structural isomerism, right? There's no structural isomerism. So let's move on. Let's go on. Next one, we have C3H8. So let's look at it. C3H8. Oh, so yes, maybe we can get something from this one here. C1, 2, 3. So we are putting single bonds because we have an alkane, right? And we have our hydrogens are the bonds that are going to be around. So you'll be saying, sir, I know definitely we would have a different structure for this one, all right? So we will say here, probably I could do it like this one here, sir, and it's going to be different. It's not the same. Okay, so you watch at it and you say, wow, they're really looking different. Now, yes, they would appear to be looking different here, but it is still the same. Why? One, there's a way in which I'm going to show you as we go later on, that helps to alleviate or make this situation a lot more easier than I would do now. So one, let me give an example for you. Now, these carbons are still connected to each other in a chain pattern. So example, it's like you have a chain and the chain is linked, and you have the chain linked out on the table, right? And these chains have links in between them, and these are how organic compounds behave. They behave similar to these, to like your chain on your neck, etc. And if I take that chain and I put it on, so now the chain forms a circle. Does that make the chain different? Does it make the chain bonded different? No, the chain simply changed the way which but the bonds are still the same. So structurally, the chain is still the chain, all right? Now, if I delink the chain and I linked it on another link, making it a T instead, then I can't, when I try to put it on my neck, I might have one hanging on here. So it's totally different than the chain that I would have had before. It's a similar case here. If I take this and I now do this, it's going to be the same here. I could do this and I could do the same thing with this. If you can imagine it with me, I could take this and I could bend it, and it's going to be the same thing. All right? So I'm going to show you exactly what are some tests you can do to ensure that the compounds that you have structural isomerism. So in this case, propane does not have any structural isomerism. I'm going to show you some more as we go down. So let's go. C4H10. Maybe this one would have. All right, so let's check it out. So C4H10, so we have 4. So what we do, we normally draw the straight chains first, and then after we do the branching, we're doing the changing up. All right, so we have 1, 2, 3, 4. All right, and there are hydrogens around. I told you I'm just not putting the hydrogens in for now. It's going to be understood just for time purposes. We am going to be leaving it like this. So, but you have to make sure and ensure that you put your hydrogens in once you are drawing your structures. So, can we have it differently? So one, I'm going to just jump the gun one time. When you are going to draw a structural isomer, I always advise my students, especially when we deal with an alkane in this case, when we get on to alkenes, I'm going to show you some more. You take a carbon, anytime you want to do something different, you take a carbon from the end and you link it to the adjacent carbon that it was bonded to. All right? The adjacent carbon of that carbon it was bonded to. And I'm going to demonstrate. So let's go back to the chain link. If I had a chain and I delink the chain, okay? And I remove this link and I linked it back on the end of the next portion of the chain. So just going to guess, I had a chain, it was long here, and there was links in between them, okay? And I decided to take the link off from this end and put it on this end. So there was a head. Would it have changed the chain? No, the chain would still link the same way. There's no change. So instead, if I had delinked the chain, so I'm just going to be putting it in this case, sorry. So if I now delink the chain, so I'm taking off this link here. And I linked it here instead. Then it's going to change. It's no longer going to be a chain as it would. It would be a chain with a branch on it. All right? And that's the difference. That's what we look at with all of these organic compounds as we go on. So in the case here, where we have butane, I would delink that chain. All right? So I'm going to erase this chain here as we have here now. So I'm going to take off the chain. And of course, if I take off this one here, I'm now going to be left with 3 carbons. 1, 2, 3. You can see I took off the carbon on the end, and now I have 3 carbons remaining. Okay? So I'm going to take that branch, I'm going to take that piece of carbon that I had, and I'm now going to attach it to the adjacent carbon of the carbon that it was bonded to. All right? So now it's going to be different. All right? So this here is not the same. All right? I can't form, if I try to bend it into a circle, it's going to always have this branch out. If I bend this into a circle, it's going to always be a circle. If I had it in this case, like some students may possibly try to write sometimes, because it appears different, it's going to always be the same. It's by taking the carbon and placing it here. But we can observe that it's going to be the same as the one above. So this and this is going to be the same. They both are the same. All right? Because I can do the same thing with this particular straight chain structure. However, this one is different and it can be observed. So what are some things that we can do to show that they are different? This is one way that you can show that they are different as well. We seek to find the longest continuous chain. What do I mean by the longest continuous chain? I would use my pencil or my pen to draw an imaginary line, all right, through the compound, all right, without making a reverse. It's like, say for instance, you're doing what do you call it? A maze, and you cannot raise your pencil and it can't go forward or backward. You need to make straight lines through. It's a similar thing that we're going to be doing here. So one, I can make a straight line through starting here, which is my first carbon, and I could move here. 1, 2, 3. Draw a straight line. Okay? So that's one way I can do to say that here's what's happening, that I have a branch here. So this is a branch in this case. Now, there's another way in which I can do it, all right, which is the same way. You can still start at, and you can do it in any direction. I could have started at this carbon and drawn and go 1, 2, 3. It's still a straight line. I didn't do any reversing. I didn't take from here and come back again. Okay? I just went a straight line. So that's same 3. 1, 2, 3. So this is now going to be my branch. Okay, so let's move ahead from here. So we can see that from 4 carbons for alkanes, you can form an isomer. So if you have an alkane with 4 carbon chains, 4 carbons within it, then it can form approximately 2 isomers. All right, you can try and you could play it up, but you're going to only be left with 2 isomers that you can get from it. So let's move on. We're not going to do 5 and 6 because there are more isomers as you increase the chain length. All right, so let's have alkane. So what have we learned so far? We have learned that carbon chains can have side branches composed of 1 or more carbon atoms. So yes, it can have side chains composed of 1 or more carbon atoms. So in this case, we had 1 chain. There is some that can have 2 carbon atoms making up the chain, and we're going to have some more of that practice as we go down later on. For this to happen, the molecule must have how much? 4 or more carbon atoms. So in order for us to have an isomerism where alkanes are concerned, we must have 4 or more carbon atoms present. So alkane isomers form by branching. So let's look at this one here. So isomers of C5H12. Remember I said we wasn't going to do this one here because it's already in. The isomers there are 3 of them. Okay? So the 3 of them, if we can just look, we can name them as well. That's another way of being able to identify whether your isomers or whether the structures that you have drawn are particularly different. All right? So by learning how to name them, you can also use this to be able to differentiate whether or not they are isomers, whether they have isomers or not. Okay? So example, isomers of C5H12, which is pentane. The first one is the straight chain one, which we will call pentane. All right? Now, the second one, we can't call it pentane because there is 5 carbons. Because it's different, we have to name it differently. So there's a method in which we are going to be going through, and then you're going to practice sometime later on, where we have this referred to as 2-methylbutane. And the last one we call 2,2-dimethylpropane. So your question would be, sir, how did you know to name these in this way? Well, there's a way in which you can learn, all right, which we refer to as organic nomenclature. You can learn how to name these compounds. So let's tap across. Let's go ahead. So naming isomers of non-cyclic alkanes. So let's look. First thing first, in naming an alkane, you must determine the longest chain of the carbon atoms. And I did give you a brief insight of how you do this. All right, so example, we have a compound here. How do we focus on the longest chain? We would isolate the ones that I can draw and a line straight in without doing any, without reversing, okay? So a continuous line throughout, and we would have this one. So we have the longest chain in this case being 4 carbons long, all right? We could have tried to go this way. Let me just see if I could draw. We could have tried to go on this way, but that would have been 1, 2, 3. And 3 is not the longest chain. The longest chain is 1, 2, 3, 4. As a result, we're going to look at we're going to focus on the longest chain. All right. Next we have indicate the carbon chain based on the number of carbons using the prefix. So we found out that the longest carbon chain is consisting of 4 carbons. So as a result, we are going to now gain the name of that long chain by using a prefix. So in this case, sometimes students have a mix-up between met, et, prop, but to find out which one. I wonder which one is 4. Is 4 prop or is 2 prop, but 2 is actually eth. So how can you remember? You remember you can use this slogan. Monkeys eat peeled bananas. So monkey, which is for met, eat, which is for eth, peeled, which is for prop, bananas, which is for but. And of course, that's 1, 2, 3, 4. And that is going to help you to remember them in the order that they are. Okay? So the longest chain in this case is going to be 4. So we are going to call this longest chain butane, because we have 4 carbons. So that's the longest chain. So let's move ahead. Naming the isomers of non-cyclic, so we're continuing. Use the suffix "ane" to indicate the compound is an alkane. So we know that part. So because of the chain, we know it's butane, so we call it butane. And we know this portion already. Because it's related to an alkane, we use the word "ane" along with the words. All right? 4. Number the carbons in the chain consecutively, starting at the end closest to the branch. All right? So the branch is the groups of attached to the main chain, which is the longest chain. So we would have established the longest chain. How do we begin numbering them? We number the longest chain from the carbon that has the branch closest to it. So in this case, this is the carbon that has, where I put the 1 here, is the carbon that is closest to the branch. I could have start from here 1, but this is not the one closest to the branch, and as a result we are going to have a higher it's going to be a little bit off. So what we do, we number them from the chain that is closest to the branch. Okay, so 1, 2, 3 and 4. All right. So one of the things that we like to apply, and we're going to apply it later on, why we do this. So, okay. Next, 5. Name and number the location of each substituent branch. All right. So the name of the substituent will be written before the main chain and will end with "il." So if it has a CH3 group, it will be methyl. If it has a CH2 group, well, 2 carbons connected in the branch, then it's going to be ethyl. So I'm going to demonstrate. So 1, we would have found out which one is the longest chain, and the longest chain is but, and we said that we call it butane. All right. So we said that, but this is not what we're looking at. We are looking at name and number the location of each substituent. So when we're talking about a substituent, we are talking about the branch chain. And in this case, the branch chain is this. And this is a carbon bonded to 3 hydrogen, which is a CH3 group, all right, which is methyl. In this case, we see C2H5. That would be a branch that is consisting of course, this is going to be ethyl in the case. So just making sure you understand what these short or condensed versions are, where we have 2 carbons, which is C2H5, because there's 5 hydrogens attached to it. All right, and we can have different ones as you go down. But we're going to be looking at the example here for today. So 1, in the example we have methyl. So because it's a branch and it is meth, which is 1 carbon, we refer to it as methyl. We add "il" to the end. So, and we would have said that the name of the substituent is written before the main chain. So butane is the main chain or the longest chain, and we would put methyl in this case here. So methyl is written before. So this is how we're getting the stages of the naming. So let's go ahead. Now, and with 2 or more side chains, you use the prefix di, tri, tetra to indicate when there are multiple side chains on the same type. So we're going to give an example. So we have 2 compounds here, and these 2 compounds contain side chains. So one, we would have said that you need to find the longest chain first, and the longest chain is the continuous one. So I'm going to start from here, first carbon, and we did say we must start with the carbon that is closest to the branch. But we have 2 branches. We have a branch here and we have a branch here. So it doesn't really matter which side in this case we're going to start at. So we're going to start at this carbon here, and we count 1, 2, 3, 4. So that's one way I could have done it. Let me check our next way to see if I have it here. So if I go from here, 1, 2, 3, 4. So I could have done that one as well. Let me see our next one. So let's see if I could go in this way. 1, 2, 3. But that's not the longest chain. So right now we have the longest chain being 4. So we're going to leave it at that. All right. So I'm going to leave the red one. So we found the longest chain to be 4. So that is actually butane. All right. Now we need to look at the branches. So the branches are what falls outside of that chain. So we have here one branch and we have another branch. So we're going to explain what this particular, this next note means. So we have this being 1 carbon on this branch. So we know this is meth. So it's going to be methyl. And this is also our next 1 carbon. So we have methyl. Okay. So what we're going to name this, we're going to have it referred to as methyl. And as they would have said, since there is more than 1, we add the prefix di-tri. So we have how many methyl groups? We have 2. We have 2 methyl branches, sorry. 1 and 2. So as a result, we have to put the word di, because di means 2. So it's going to be dimethyl. All right? And we need to note the numbers that they are according to the last slide. So the numbers we have, we're going to number them. Let me see if I could use another. So we have 1, 2, 3, 4 carbons. So we have the methyl being, one of the methyl being on the second carbon and the second methyl being on the third carbon. So we will call this compound using the numbers 2, 3 dash. So we always put a dash in between names. So we have 2,3 dimethyl butane. So let's look at the next compound as we apply all of these. Straight chain 1, 2, 3, 4. That's the longest chain I'm seeing. And I'm seeing 2 groups here again. So I know that this is going to be dimethyl. All right, because there are 2 methyl groups. And of course, this chain is called butane. Butane. So these are isomers. And let's look at the number. We begin numbering from the busiest end. All right, and the busiest end is on the right side. So let's look at, we have 1, 2. So the carbons are on 2. So how do we name this one in this case? We say 2, 2 dash dimethyl butane. All right. And we're going to have some more practice as we go on. 7, we use commas to separate each number and hyphens, just as I would have done in the example before. So you would have seen me using the commas here. All right, in each case, to separate the numbers and the letters. And of course, hyphens to separate the letters. All right, and you would have seen me using a hyphen in the case to separate the numbers from the letters. Okay? So a comma to separate the numbers from the numbers, and a hyphen to separate the numbers from the letters. And you name the side chain in alphabetical order. And that's, of course, when we get a little bit more complex compounds, and there's where we're going to have to put in practice. So this is where we now can apply how we name this compound. So for the first one, we know the long chain. We find the long chain is only a long chain. There's no branches, and there's 5 carbons, so we call it pentane. All right, so we're dealing with alkanes here. Next one, we look for the longest chain again. The longest chain, we start from the busy end. So we have 1, and we have 1, 2, 3, 4. So this has to be a 2, and we have a methyl group here. So it's going to be butane and a methyl group, and of course we have to state the number what it is. 2-methyl butane. 2 because it's on the second carbon, that's the branch, and methyl because it's a methyl branch that we have, a branch consisting only of 1 carbon. And let's look at the next one, 2,2-dimethyl propane. Why? Because anyway we could take it from here, 1, 2, 3, all right, and the branches of course are going to be these 2. So we have 2 methyl branches, and we learned that when we have 2 of the same branches, we use di, tri, tetra, etc. So 1, since di is 2, we use dimethyl to say that we have 2 methyl branches, and the carbons that they are attached to is 1, 2, it's the second carbon, so we say 2,2-dimethyl propane. Please note this. A lot of questions may come. Why do I have to say, I could have just said 2-dimethyl propane. Now, in order to have things done properly and to avoid mistakes, that's one of the reasons why we would keep this particular way. So we move ahead, and we are closing off now. We have some practice. So, name the following alkanes. How do I name this? Okay, so let's find the name. So remember, we have to find the longest chain first. So the longest chain we can count, and we begin from the busiest end. So I can have, and it's important to note that we try to have our branches having the lowest possible number, right? Lowest possible number when giving it its name. So let's find the longest chain. 1, 2, 3, 4, 5. So 5 here is the longest chain. If I go here, 1, 2, 3, 4, of course, it may not be the longest chain. 5 is the longest chain in this case. So since 5 is the longest chain, I know my longest chain is pentane. So I can write this out. What are my branches? I have 1 here and have a next one here. So this is called pentane. All right, the long chain is pentane, and these here are methyl groups. So what happens in this case? We have 2 of them, and since we have 2 of them, we have to say dimethyl. All right, we have to add numbers, and we separate words from numbers by putting a hyphen. And the numbers that they are found on the chain, we have 1, 2, 3, 4, 5. So, or we could have gone this way, 1, 2, 3, 4, 5. But here is a problem. Here we're going to have the number 3 and then 4. But in here we have 2 and 3. So we want to keep the one that has the lowest number. So as a result, we are going to have, in this case, 2, comma, we separate the numbers with a comma, 3. And there we have it, 2,3-dimethyl pentane. And that's the name of this compound. So let's look at the next one as we go ahead, as we put our practice in. So again, first case, find the longest chain. And the longest chain, let's say we are counting here now, the longest chain. 1, 2, 3, 4, 5. Is that the longest chain? Let's check. We can check another way. 1, 2, 3, 4, 5. Same 5 if I go up. 1, 2, 3, 4. So 5 is the longest chain, and I'm going to keep it at this one. What are my branches? 1 branch here, 2 branch here, 3. These are out of the line. So we have 3 branches, and they are all consisting of 1 carbon. Being consisting of 1 carbon, we refer to them as being methyl branches. And it being a methyl branch, and we're having 3 of them, we will use the word tri. So we're going to call them trimethyl. Okay? So we have the last part of the name already, the longest chain, which is 1, 2, 3, 4, 5, which is going to be pentane. Now we are looking at the branches now. We are going to say trimethyl. And now we're going for the numbers. The numbers now, we have to put a hyphen to separate the numbers from the letters. And we have the numbers now. So let's count. Let's see if we can have. So I'm going to start to count from this end. 1, 2, 3, 4, and 5. Okay? Let's check our next direction. Let's count from here. 1, 2, 3, 4, and 5. So we want to have the lowest possible numbers. And the numbers here that we have, we can have them as 3-3. That's it counting in this way here, because 2 of the methyls are on the 3rd carbon, and then we have a comma, 4. Or we can have it as 2, 3, 3. That's going in the other way. So the numbers, we said that we seek to get the lowest possible numbers. So this is the one that we are going to use, which is the one that is in green. All right, I should have. So this is the one that is in green, the number system, and this is the number system in blue. All right, so we're going to prefer to use the numbering in green because we have lower numbers that way. So as a result, our name is going to be 2, 3, 3 trimethyl pentane. And there we have that example. So let's try one more for the road for this one, and then we're going to have one more example before we close off. Let's look at this one here now. So we have another compound, and we need to find the longest chain first. Always find the longest chain. So let's try here. 1, 2, 3, 4, 5. Okay, let's try the other way to see if we can get it. 1, 2, 3, 4, 5. So either way we take it, it's going to be 5. So we're going to keep it in that direction. So let's find out the name of this compound. So the longest chain is 5. I'm going to so we have 5 is pentane. All right, and our branches are going to be consisting of how many carbons? This is our branch. But our branch in this case contains 2 carbons. And when we have 2 carbons, this is 1, 2, we call it eth. So it's going to be called ethyl. All right? So we would add the word ethyl. And there's only one ethyl branch. There's not 2, there's only 1. All right? So if there was 1 somewhere else on the compound, then we would have possibly taken it. But in this case, it's only 1 ethyl branch. So we draw our line and we look for the number. And we're going to number them now. 1, 2, 3, 4, 5. It's going to be the same thing. 1, 2, 3 if we do it in the next direction. So our number system here is going to be 3-ethyl pentane. Again, 3-ethyl pentane. So let's look ahead now. So this one here is asking to draw the following alkanes. So having this information, we're going to be doing it in reverse. So doing it in reverse now, let's look at this name. So we know from this portion here that the last name is the longest chain. So one of the practice that we do, we draw the longest chain first. So pentane, 1, 2, 3, 4, 5 carbons. All right, so we know these carbons are bonded in different ways. Bonded single bonds to other elements. Okay, then we have the branches. Dimethyl. I'm going to use a different color to illustrate this. So we have dimethyl, and we know the word di, which tells us that we have two methyl branches, and the numbers tells us exactly where they are on the second carbon. So we're going to count 1, 2. So they are on the second carbon. So I'm going to put one here, and I'm going to put the other adjacent to it. All right. So opposite to it. Okay. So 1, we have this being our compound, and of course we are going to put our hydrogens in. You have to make sure you put your hydrogens in all the time to complete your compound. All right, so I'm not going to continue because it's a lot of hydrogens in this case. But make sure that you do it in your time. So this is our compound. This is how it is drawn. Hydrogen here, hydrogen here, hydrogen here, and this is our compound, 2,2-dimethyl pentane. Let's look at another one. All right, so we are almost coming to a close. So the next compound we have, look at the name and make sure you look very carefully at what the name would consist of and what we will look for. We said we will look for the longest chain first. And in this case, the longest chain is butane. Being butane, we know that we are going to put 4 carbons out. 1, 2, 3, 4. And we want to have our branches now, which is trimethyl, which means that we have 3 methyl groups. And the number tells us where they are. 2,3,3 trimethyl. So I have 1 on the second carbon. 1, let's count them out, 2 and 3. Okay, so I have 1 methyl group on this carbon here. I have 2 of them on the third, so 1 on top and the next on the other side, and that is my compound right there. Again, make sure that you put your hydrogens in. They are very important. Always have your hydrogens in. In this case, because of time constraints, I'm just leaving it at that to demonstrate. So last example. So we have this one here, which is 2,3-dimethyl hexane. So 2,3-dimethyl hexane. How am I going to draw this one out? I can hear you. I know you are saying here, sir, you need to first look at the longest chain, and the longest chain is hexane. Longest chain being hexane, we have 6 carbons. 1, 2, 3, 4, 5, 6. All right, so this is a long one. All right, and we're looking at the branches. Dimethyl, so we have 2 methyl branches. All right, and they are on the 2nd and the 3rd carbon. So we have a methyl here, and we have a methyl here. And that's it. Compound is done. Make sure, of course, you put in your hydrogens. Very important. Okay, so before we go, there's a little challenge. So this looks crazy. This is, you will say, so what is that? So I like to challenge my students a little bit. Taking the challenge on is something that is very important. Applying the concepts that you would have learned. All right, so we did show about a line structure and what it means. And we said that on the angles and the ends, well, in this case, this end has a carbon. The carbon is shown there, so we don't have to recognize it as a carbon on all the ends that we have here because there are carbons that are showing there. But the angles, which are these areas, are the ones that are going to also consist of your carbons. So let's take a look at this particular example. So they're asking you to name this compound. So what is the first step? So we need to find the longest chain. All right? So we need to find the longest continuous chain. So 1, let's begin. So we see that the numbers coming in here, 2, 3, 4, 5, 6, 7, 8, 9. But before we go, let me see if we can work this out together. All right, otherwise. So this is a chlorine, so this is not a carbon. All right, so we're not going to start there. We're going to start, and of course we want to start on the busy end, and we have 2 groups here. So we're going to start on the busy one. All right, so we're going to have here 1, 2, 3, 4. That's definitely not the longest chain because I can make a longer continuum. 1, let's try a next one, beginning from that same carbon. 1, 2, 3, 4, 5, 6, 7. Okay, so that's another one that I could have had. But let's check to see if I can get longer. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 seems to be the longest chain. And that's why we would have done this numbering system. So the longest chain consists of 9 carbons. 9 carbons. So having 9 carbons, we will name it nonene, as is shown on this side here. So nonene. Let's move on. So outside of those are going to be your groups. So we have our groups now. So we have 1, 2, we have 2 methyl groups, right? CH3 is a condensed way of writing the C with the 3 hydrogens connected to it. So we have how many of them? 2. And since there are 2, we're going to refer to it as dimethyl. And there's a next one, which chlorine, and we refer to chlorine as chloro in this case. All right? Any bromine, any halogens connected to a chain forming a branch, we will say things like bromo, iodo, chloro, etc. All right? So we have them. So let's see if we can construct the name now. Okay? I believe we can. All right? So 1, the last name, the name comes first. So the position of the substituent groups are specified by numbers. So the numbers, based on the numbers, tell us the position. And we also have to write these groups in alphabetical order as the last time would have said. So we have, you could have gone this way, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or we could have gone the other way. So we prefer to go this way and not the 191, because the 191 does not give us the lowest possible numbers. So we're going to keep this one the direction that we have going here. So following from there, we can construct the name. Because we have two constituents of the methyl, we refer to them as being dimethyl. So the compound's name is going to come up with nonane, which is the last portion of the name. We have chloro and methyl, and C is before M, all right? So because of that, we have chloro being the first one in terms of alphabetical order. But we have two methyl groups, so we call it dimethyl. Where are they located? Third carbon and the sixth carbon, that's why we have 3, 6. And chloro is found on the second, so it's going to be, and if you notice, numbers separated by a hyphen from the letters. Let me just erase that. So numbers separated by a hyphen and from letters, and your numbers are separated from each other by a comma. All right, and there we have it. So this is the end of today's presentation. I would like to thank you for joining us today. All right, I hope that this was a productive session for you and you did learn a lot. I pray that through these sessions that you would be able to learn more about organic chemistry and that you would do well on the exam that is ahead for you. As I always say, stay sharp. And from the Division of Education, Innovation and Energy, we thank you for joining us today and do have a wonderful week. Till we meet again, stay sharp.